Good morning or good afternoon, depending on where you are at. My name is Atarod Azizi Namini, Director of the IBT ABCUTC at Florida International University. So very warm welcome to more than 600 people who have signed up to listen to our October 2024 monthly webinar live. We are delighted to bring to you a topic that is very close to bridge engineering related to the corrosion. The title of the webinar is Galvanic Concrete Encasement for Accelerated Repair and Service Life Extension. We are delighted to have with us a very familiar face to the bridge engineering community, David Whittemore, who is President and the Chief Innovation Officer for Vector Corrosion Technologies. During the registration process, we have received some questions that we're going to try to, as time permitted, to address them. But by all means, if you have some additional question, please post it on the dashboard and we'll try to get to them as time permitted. A couple of important news. The 2024 World Bridge Engineering Conference is right around the corner. It's going to be held December 11, 12, 13 in Hilton Hotel in Miami, downtown Miami. We have an award program. There's going to be award in 6 different categories. 3 of them are related to recognizing individuals that have contributed to the bridge engineering, and 3 of them are related to the projects. The deadline to submit applications is November 8th. Please, if you have a project that you think is deserving an award, or individuals that you feel like that should be receiving recognition, please go to our website and submit the application before November 8th. Again, 3 different awards recognizing individuals and the 3 awards recognizing projects. Registration is open. Please register early. Also, we had reserved some room block for the conference. All the rooms are gone, but we are talking to the hotel to give us some additional block of rooms. So hopefully by Monday, we will have some additional room blocks at the special conference rate. So please check again next week if you were not able to reserve your room. There is still opportunities to exhibit at the conference. There are still few booths that are left, so take advantage of that. Conference again is sponsored by 32 state DOTs. Of course, the conference is sponsored by U.S. Department of Transportation through our University Transportation Center, IBT ABC-UTC. Conference includes 9 keynote talks covering different topics. You can go to our website. You can look at the keynote talks. The conference program is ready. You can go to our website. You can take a look at the detailed description of the presentation that are going to be made. The conference includes, other than the keynote talks, 140 half-an-hour technical presentation. So it's very rich. And there's going to be one workshop on shotcrete with ultra-high performance concrete that we know that lots of interest in that. That workshop is going to be held on Thursday evening, basically. Also Wednesday evening, we are going to have a reception and the entertainment. So with that, let me turn it to Kathy, who is going to be sharing with you some additional news related to the bridge engineering and the innovations. Kathy?
Thank you, Atorad, and thank you all for joining us for the 163rd webinar in our monthly series. Before we get started, I'd like to share some upcoming events with you from both the IBT ABC UTC and some of our industry partners. First, and this is just next week, but I wanted to keep this on here, the ASBI, the American Segmental Bridge Institute, will be having their 36th annual convention and their committee meetings next week, October 20th through the 23rd in Atlanta, Georgia. For more information, see the links on the screen. Next is the Precast Prestressed Concrete Institute, PCI. Their annual convention and the Precast Show is from February 3rd to the 7th in Indianapolis, Indiana. For more information, you can see the link on the screen. It's surprising that we're already talking about things in 2025, but there we are. Our next event is the AISC NSBA, the Steel Conference, which is it includes the World Steel Bridge Symposium. That will be in Louisville, Kentucky on April 2nd through the 4th of next year. I don't have 2025 on there, but that is in 2025. So for more information, you can see the links on the screen. And now to IBT, ABC, UTC upcoming events. Next month, we'll be featuring Michael Como. Many of us have seen him speak before. He's a fantastic speaker. He's going to be talking about observed long-term performance of prefabricated deck level connections. This will be a great presentation. It's actually looking back at some of the projects that we've presented many years ago as part of this webinar series and really tracking how they've performed over time. So please join us for next month's event, October 17th. And next week on Friday, October 25th, we'll be having a research seminar. The featured project is large-scale implementation of semi-proprietary UHPC with virgin and recycled fiber for full precast bridge columns. We'll be presenting, this is being presented actually by, I'm sorry, but it will be a presentation next Friday. Thank you. So now we'll get to today's featured presentation. Before we get started, a few housekeeping announcements. First, this training is being recorded and it will be posted on the IBT ABC UTC website in the section titled Monthly Webinar Archives. Second, a PDF version of today's presentation is provided in the GoTo dashboard on the right side of your screen. You can download these PDFs during the training session, but they will also be posted in the archives referenced above. Lastly, all presentations will be followed by approximately 10 to 15 minutes of question and answer. Please enter any questions you might have during the presentation in the question box in the GoTo dashboard. So our presentation for today is Galvanic Concrete Encasement for Accelerated Repair and Service Life Extension. We welcome David Whitmore from Vector Corrosion, and now I will turn the presentation over to David.
Thank you very, very much for the opportunity to come and present today. Welcome to everyone who's joined on to the webinar, and it's a privilege to be here to talk a little bit about galvanic concrete encasements and how they can be used for accelerated repair and service life extension. Today, I'd like to go through a few different things, and I'll just give you an overview or an outline of what I'd like to go through here in the next 45 minutes. And first, I'd just like to talk very briefly about the advantages of accelerated repair and service life extension. Second, I'd like to just explain what is a galvanic encasement so that we have a good understanding of that. And then third, which will be the main portion of the presentation, I'd like to show you some galvanic encasement project case studies. And finally, I'd like to close out the seminar by just talking a little bit about environmental issues and the sustainability benefits that can come from doing these types of repair and service life extension projects. So with that, we'll just get going. And I thought I'd start by showing a picture of a bridge. There are a lot of structures out there which suffer from deterioration, and very often those structures end up being demolished and replaced. And that may not be the most beneficial option for either the owner or the traveling public or society as a whole. but that does happen quite a bit. And there are a lot of advantages of accelerated repair and service life extension. And this is not an inclusive list, but generally this is lower cost than replacement. If not, then probably you should do replacement. Generally it's faster than replacement. Generally there's much less impact on traffic and you have improved work zone safety issues. Often you have reduced environmental permitting. You certainly use less material and as a result have a lower environmental impact. And finally, you know, all of these things lead to improved public relations, and hopefully not only the public is happy, but so is the owner and contractor and everyone else. In order to do this, however, we need to be able to do repairs that last. Okay, and there are a lot of repairs out there that are done that are maybe not done very well, and as a result of that, they don't last. And you know, if you're counting on the repair to last, you know, doing it poorly or not doing the proper things in order to make a durable repair are not good. So this is a picture of a beam end on a bridge by a leaking joint, and you can see they've done some repairs. They haven't done many of the things that should be done in terms of detailing of the repairs, and the repair is failing, obviously failing, and very often fails after a short period of time. There are organizations out there like the International Concrete Repair Institute, which produces and has available a number of different guidelines and procedures for doing different types of concrete repair steps. This document that I'm showing here is specifically related to how to do proper concrete repairs. And for your information, ICRI, or the International Concrete Repair Institute, is part of the National Concrete Bridge Council, and so you can access a bunch of their documents. So in this document, for example, it talks about how you should have square cut edges, you should chip around in behind the reinforcing steel, and a number of other things in terms of surface preparation and getting a nice, clean, rough, sound surface to bond to. And even things like the shape of the repairs, instead of doing ragged shaped repairs. And let me just get my pointer going here. Here. So instead of doing ragged shaped repairs just to follow around the area that's damaged right at the moment, you're much better off, and it's outlined in this document, to do nice rectangular or square shaped repairs. You'll have a lot less issues with cracking, and you'll have a lot better quality control and durability. And a whole bunch of these things are outlined in these documents, and I highly recommend using that. If you do that, and this picture here in the top right corner shows some repairs done by Virginia DOT on a bridge deck just outside of Washington, D.C. And they've followed basically all of the recommendations of the ICRI guideline: good square cut edges, chipped around behind the bars, good quality repairs. And so if you follow those procedures, the repair itself will be fine. But the issue, if you do good quality repairs, you can make the repair itself last, but that doesn't mean the overall structure is going to last, because if you do this type of repair, even if you do good repairs, you can run into a situation where the area adjacent to the repair continues to corrode, and you end up going out and doing more repairs and then come back and do more repairs. And we refer to that as patch accelerated corrosion. And so even though the repairs themselves might be done well, you can still have an ongoing corrosion problem that causes a maintenance issue. And why does this happen? Well, it happens because when we do a repair on a deck or a column or a beam, we remove a section of concrete and replace it with chloride-free concrete, but we leave chloride contaminated or possibly carbonated concrete around the perimeter of the repair. And over time, the corrosion will continue, or in some cases even accelerate, in the immediately adjacent area where you've left chloride salt contaminated concrete. And that happens because you have different potentials, or essentially voltages, in the steel, which result from the environment around the steel. So where you have salt contaminated concrete, you may have a potential something like minus 350 millivolts, whereas in the concrete without chlorides, you might have a potential of only minus 200 millivolts. And you have a voltage difference here. And the area that's more negative is always the area that's going to corrode. And that's going to push current to the area that is being protected by the corrosion. And so that's the mechanism that happens in the background. We can address that mechanism locally by putting a galvanic anode into the repair. And even though we still have chloride-free repair and we may still have chloride-contaminated concrete surrounding, this will either slow down or completely stop the corrosion, because this anode will have a corrosion potential that's much more negative, something around minus 1100 or minus 1000 millivolts. And that's more negative than the steel in the chloride contaminated concrete or the steel in the repair itself. So current is going to flow from the anode to the steel, and the steel is not going to corrode as a result of that. And that's just because, again, you've got these voltage differences, and the most negative thing is what's going to corrode, and current's going to go from the more negative thing to areas that are less negative, as indicated here. Now, in terms of a galvanic encasement, we're doing very much the same thing, except that we're doing it on a distributed or a kind of a global, or at least an area basis. So instead of just having a single anode to protect a very localized area, we have a distributed anode that might be applied over the whole structure or section of the structure. And that anode is passing current to the steel, even in the areas where you have salt contaminated concrete remaining. That steel is protected and will either stop corroding or corrode at an insignificantly slow rate in the future. So that's the concept behind a galvanic encasement. And just to illustrate before we get into the project examples, on the left-hand side here, you see an example where you have localized galvanic protection, some local galvanic anodes installed along the edge of repairs, joint repairs, and concrete repairs on a bridge deck. On the right here, we see a galvanic encasement. During installation, you have galvanic anodes, these vertical strips, applied over this whole area for our New York State DOT. And one is localized protection, the other one is more global, or a whole area that has been identified to be protected. One other thing I just wanted to touch on before getting into the case studies is that I had the really good fortune about 15 years ago to be involved in a research project, a strategic highway research program number 2, SHRP2 program project called R19A, which had to do with design of bridges for service life, and specifically for service lives beyond 100 years. And I had the good fortune to work with Atarod on that project and a number of other really good people. And this project was focused on, well, not really focused on, it had two main avenues. One is, how do we design new bridges to last 100 years or more? And a lot of people you talk to when you ask about this project, that's the part that they're really familiar with. But there's another part of this project that related to, what do we need to do? How can we design repairs to existing structures so that we can extend their life to last 100 years or beyond? And there are some good resources available. The link to this guide that's shown on the right is shown here. And I'll refer to it in a couple places during the presentation. But we're going to focus on this second point here, which is, how do we design repairs to extend the service life of the structure to whatever age we want. And so when we talk about repair design, it all depends on what's the condition of the existing structure and what are you trying to achieve. So in very, very simple terms, if we break down what's in R19A, for existing structures, if the structure itself is in good condition and the desired service life or service life extension is not too long, you might not even have to do anything at all, or maybe you can do a treatment like a coating or something to keep the concrete drier to slow down the corrosion rate. That is certainly a possibility. But if the condition of the structure is in poor condition already, or if the deterioration rate is already high, or if you want a really long added service life, then you probably, in most cases, need to do something more significant than doing nothing, or maybe putting sealer on the concrete. And it may involve going in and removing and replacing all of the existing chloride contaminated concrete, for example. It could involve using some form of cathodic protection, either impressed current, where it's a powered system, cathodic protection, or galvanic, which is obviously where you use galvanic anodes of some form. That's what we're going to be talking about today. And or it could be where we're talking about using some form of electrochemical treatment like chloride extraction or realkalization for carbonated concrete. But you probably need to do something in order to get the service life, because otherwise the structure is going to continue to deteriorate, and that won't get you to where you want to be. There is a graphic in the R19A document that I showed you the link to that specifically relates to options for structures, bridge structures that are already corroding. And it kind of highlights, it's a little flow chart here, highlights those options that I showed in the last slide. So if it's not too severe, you're kind of on the left-hand side of the chart over here. And as you get more severe, you probably move to the right, or at least you look at the options that are more on the right. And the option that we're going to be talking about today in these examples is using galvanic cathodic protection. And that's where you don't have an external power supply. You simply have some form of galvanic anodes that are installed and connected directly to the steel. Okay, so into case studies, examples. I thought I'd start with a case study example that is actually in the R19A report. This case study is on a deteriorated bridge abutment. It's actually a whole series of bridge abutments, but what's illustrated in R19A is a single abutment. And Ohio DOT, which was the owner here, wanted to extend the service life of these abutments because they had put new decks on these bridges a few years before, and they hadn't done anything to address the substructures. They thought they were good enough at the time. Now the substructures were in bad shape, and they had a bridge deck on top that had a lot more life left in it, so they wanted to deal with the substructure. And so, as outlined in R19A, it is certainly possible to extend the service life beyond 100 years. There's no issue about that. But you do need to consider what is the existing condition. You need to consider the existing materials. You need to consider their, what's their physical condition, what's their degree of contamination, what's the condition of the reinforcing steel in there, and you have to consider it as a whole in order to have a holistic design. And so here's a picture of the first abutment that's there, and you can see that it's clearly exposed to a leaking deck joint and chloride contamination. There's cracking, may not be completely spalled, but these chunks of concrete all along the edge here are loose, and it's clearly not in good shape. The solution that Ohio DOT did, this is a job that was done back in 2005. Basically, I'll show you through a series of pictures, but they essentially removed the existing cracked and damaged concrete that you could see in the previous photograph, and they put a new layer, 6-inch thick layer of self-consolidating concrete over the entire face of the abutment with new reinforcing steel and dowels. And they specifically put in distributed galvanic anodes, illustrated here, into that refacing. And the reason they did that is because they were leaving all of this yellow chloride contaminated concrete in the structure. They weren't removing it. And the reason they weren't removing it is because this bridge was in service and they wanted to do these repairs without having to shore the structure or take the traffic off the structure or any of those kind of things. So they removed the existing damaged concrete, but they did not remove all of the chloride contaminated concrete in the pier. And because they weren't doing that, they knew that if they did this refacing, the refacing would be fine, but this steel back in here would all continue to corrode and would fail the refacing after a short period of time. So they put in the anodes to protect the steel that remained in the salt contaminated concrete that was left in place. So just to walk you through a few photographs, you can see the steps. So the first step they did was to go and remove the existing cracked and delaminated and spalled concrete. You can see that has been removed, and it's mostly at the top edge where you can see all the damage in the previous photo. They did not remove all of this salt contaminated concrete down here. They did not remove the salt contaminated concrete behind the cracked section because they're still relying on it to carry the load of this bridge deck. They then went and put in dowels and a new cage of reinforcing steel, and the galvanic anodes in this particular case are these red bars here, 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 and you can see they're distributed along the whole section that they're doing, and those anodes are electrically connected together. You can see the wires here, and the wire goes from this to connect to the steel in the existing structure. Okay. They then formed the front face of the abutment, and because this was at the time the first job of this type that they had done, they put in some monitoring stations so they could monitor the performance long term. The concrete was poured, and now here you can see the completed repair. The forms have been removed. Essentially new concrete facing on this wall, but inside that concrete facing are the galvanic anodes that are connected to the steel inside, and this monitoring box here allows the owner or us to be able to go back at any time in the future and take measurements. Like I was saying before, this job was done in 2005. It's been monitored from that time going forward. You can monitor many different things. They did some continuous monitoring at the beginning with a data logger, and they were monitoring. The orange line is showing the temperature of a thermocouple that's embedded in the concrete. So this is summer, winter, continuing along. And the blue line is measuring the current that's going from the anodes to the steel, and that is high in the summertime and lower in the winter, higher in the summer, and continues along. But you'll see that it doesn't go to zero even in the middle of winter. Even though the temperature is getting below freezing in the middle of winter, it's still actually passing current to the steel. And probably more important than all of this is that they have been monitoring since 2005 a parameter called polarization, which is the main thing that you measure when you want to determine if a cathodic protection system is working or not. And the NACE, or National Association of Corrosion Engineers, standard for cathodic protection is that the polarization needs to be 100 millivolts or greater. And if it is, then you can sleep easily knowing that the steel is cathodically protected and not corroding. And the polarization for this structure has been well over 100 millivolts from 2005 up to over 17 years, and continues to function. And the other thing that they can monitor by monitoring the current flow over time is how much additional life, how many more years do you have out of the anodes. And based on their monitoring, they're going to get an additional 35 years of service life based on the anodes they put into the abutment here. So that's one example, and I just use that. It's quite a small job, but Ohio DOT has now used that same technique on over 30 projects, and so they're using it regularly on some very small bridges and some bigger ones, but I thought that it would be interesting because it goes back to the SHRP2 R19A project. The next project that I was just wanted to show you is the Ministry of Transportation of Ontario did a series of rapid bridge replacements starting in 2000. First one was in 2007, and the last one was done in 2012 up in Ottawa, Canada. Basically these were bridges. The expressway is up here, and these are all underpasses underneath the expressway. And you can see, I guess similar in a way to the Ohio job, signs of leaking joints, and obviously the concrete abutments here and wing walls are not in the best shape. And the deck of this structure is not in good shape either. The substructures, they used a galvanic encasement. This was the first job of this type that Ontario Ministry of Transportation did. And so they went in, removed any of the delaminated concrete. So you see localized areas here where you can see the reinforcing steel has been exposed. They've roughened the concrete surface. They've put in dowels. They're going to put in rebar, a new cage of rebar. They're going to put in the anode similar to the previous example. And they form and pour the abutments and the wing walls back, but they leave them in service because traffic is on here during this whole process. The superstructures in this case were removed and replaced using accelerated bridge construction methods. If you look in the lower right-hand corner here, here's a picture. This is the bridge down here. It's on askew down here. They actually built the two new superstructure units in a temporary yard that was built just off the end of the bridge here. And then they used heavy lift equipment to transport those new deck sections, total superstructures, and replace the bridges down here. So each of these two bridges were replaced in a 16-hour road closure, and they dropped the new ones in place on the substructure that at that point had already been completed. And here you can see a picture of the rehabilitated or reconstructed structure. So this section up here is new. That's the new deck that was dropped in, and everything, the abutments and the wing walls are the original old structures that were rehabilitated using galvanic encasements on both sides. And like I said, Ontario did this series of structures and using rapid bridge replacement, and they have continued to use the galvanic encasement technique for substructure repairs in a number of other projects as well. Okay, move to a completely different kind of structure. This is a tunnel project. This is a project that's actually going on in Montreal right now. The first phase of the project, the first tunnel, it's actually two parallel tunnels that go from the city of Montreal underneath the St. Lawrence River to the South Shore. It's the most heavily trafficked tunnel in Canada. And the picture that I'm going to show you are from the first tunnel, which they finished the work on earlier this year, and they're just switching over to start the second tunnel this winter. But here's a picture at the north entrance, where you're driving down into the tunnel, and you can see along the walls before it goes underground. you can see some localized damage, but unless you go out and do a hammer survey or whatever, it maybe doesn't look all that bad. And then over on the right is essentially the same section, or just up from the same section. And you can see there's a lot of delaminated concrete there that was removed, obviously prior to the concrete replacement work going on. Down inside the tunnel, here you can see a couple of images. You can see, obviously after the roadway is removed, and the tiling from the walls was removed, and they've done some surface preparation. It's not in the greatest of condition, and all of the issue here is chloride-induced corrosion because of salt spray, because of the cars and trucks going through here, just create a salt mist in the air that settles on all the surfaces. And on this particular project, they're using galvanic encasements for the walls, which show you a couple of photos here, as well as for the underside of the ceiling, the roof of the tunnel. And so the photos that you see right now on the right is a picture of one of the wall sections after the hydrodemolition is done. And you can see the prepared concrete surface. In some places, the reinforcing steel, the outer layer of reinforced steel is exposed. In some other cases, it's not. They're putting in dowels and a new cage of reinforcing here. These are the anodes in this case. There's one there, there's another one there, here's another one down here. They're kind of put in on a grid pattern over the wall area. They're using these massive forms, and they're basically forming a 100-foot long section of wall all in one section. They have hydraulics and a rail on the bottom for moving along the length of the tunnel. They set them in place, and then they pump the basically self-consolidating concrete in behind the form. And on the ceiling, they're doing basically the same thing. After the hydrodemolition, they're putting up new reinforcing steel and dowels. You can see the galvanic anodes installed here, one here, one here, one here, kind of essentially on a grid pattern. And for the ceiling work in the tunnel, they're doing basically the same thing as the walls. They have a 100-foot long section of forms that are automated and roll along inside the tunnel. And then they have these edges that the whole thing can be set with hydraulic cylinders, and the edges can push up to seal on the edges. And they basically pump those repairs as well. And then obviously they just keep moving along down the tunnel, 100-foot section at a time. And here you can see a completed section of the tunnel. All of the concrete work for the walls and the ceiling is done. You have a new concrete surface for the walls and a new concrete surface for the ceiling. And as with the two previous examples, the galvanic anodes are buried in this new concrete wall and underneath in the roof. And the purpose of those anodes is to protect the steel that remains in the salt contaminated concrete that is remaining there, to keep that from corroding for the design service life. Obviously, if they went in and removed all of the chloride contaminated concrete, they wouldn't need to do any galvanic or impressed current cathodic protection. But based on my discussions with the engineers, the issue was if they removed that much concrete, the tunnel section wasn't structurally stable anymore, and so they had a huge structural problem to deal with. Okay, now I'd just like to move to, this is actually the last case study today, and this is a project in Toronto. It's called the Gardner Expressway. It's actually owned by the City of Toronto, and it's It's a very heavily trafficked, elevated expressway that goes through downtown Toronto. And I'm going to show you two videos to kind of lead into this that were produced and published by the City of Toronto. And I have to give the City of Toronto a huge kudos for the amount of communication and the transparency that they have had with the public in terms of their issues and what they're trying to accomplish by this project. The first video, I'm only going to show you a portion of it because it's several minutes long, but you'll get the idea, and then I'll show you the second one, which is what their strategy is for the repairs. So here's the first video.
Since 1955, over 60 years, the Gardiner Expressway has been a major transportation artery in our city, a vital thoroughfare for commuters, businesses, and the traveling public. This highway has been an integral part of our transportation network, critical to supporting the growth of our economy and a multitude of industries operating globally. However, as the structure ages, the bond between the surface layer of concrete and its reinforcing steel breaks down. As a result, incidents of loose concrete falling from the structure have increased in recent years. And it's important to know that while the city is addressing this issue with proactive measures, such as removing the loose concrete and regular inspections, the expressway is structurally sound.
Okay, so that's the first video, and that gives you a little bit of insight into the problem. And I'm going to show you the next video, which is their strategy for solving it. And this is a public information video that they have. It's available on their website.
The Gardiner Expressway is over 60 years old, and the section between Jarvis Street and Cherry Street is nearing the end of its service life. This is the #1 priority and first project of the City of Toronto's Gardiner Expressway Strategic Rehabilitation Plan. What does this work involve? The entire concrete deck and steel girders of the expressway between Jarvis and Cherry will be replaced. The westbound off-ramp at Sherbourne Street and the eastbound on-ramp at Jarvis Street will also be replaced. And the westbound off-ramp leading to Yonge, Bay, and York Streets will be extensively repaired. What does this mean for drivers? During construction, 2 lanes in each direction will remain open throughout the expressway work zone. There will also be full closures on the ramps in this area. However, only 1 ramp will be closed at a time. From time to time, there will be closures on Lakeshore Boulevard outside of rush hours between Jarvis and Cherry Streets as crews work to remove and replace sections of the expressway deck above. This major work is using accelerated bridge construction methods, and crews will work around the clock to complete this project as quickly as possible. During construction, please plan your travel in advance. Be patient, obey signs, expect delays, and consider public transit. Thank you for your patience during construction. You can learn more about this work on the city's website at toronto.ca/Jarvis to Cherry.
There, I hope you enjoyed those videos. And as I was saying, I don't know another owner that we've worked with that's been more transparent with the public in terms of the issues and their strategy going forward. The videos give you a background, but I'm going to show you a series of pictures here to show you the work that's actually going on. So this is in phase 1 of the project that was referred to in the videos. And here's a picture of the existing or the pre-existing condition of the substructure units. And you can see that there's a lot of damage. This is before concrete removal. There's obviously delamination and spalling. You can see clearly signs the joints have been leaking, and it's led to issues with the substructure. So these are not pristine, brand new things that are just being, touched up. They're in fairly rough condition from a concrete point of view anyway. And so this image is from the one of the bid documents for the job. And basically what it's showing is a section through one of the columns And essentially, the work involves removing the existing concrete cover down to the depth of the top layer of reinforcing steel that's here, shown by the dotted line. They are not chipping behind all of that steel unless the concrete is already spalled or delaminated, in which case they are, but generally they are not, because they are, at least from what I understand, well, the structure is remaining in service during this work, and they want to maintain the confinement of the concrete core. They're putting some galvanic anodes in a vertical orientation on the columns and in a horizontal orientation on the pier caps. And then they're forming and pouring the concrete back to slightly larger than the original dimensions, but effectively they look the same as before when they're done. It's about 1/2 inch bigger in each direction. And so just to show you what this looks like on kind of during the work, here's a picture taken during construction. You can see the column here on the right and the column left on the left. You can see the columns have been, the work has been completed. So the cover's been removed, the anodes have been installed, the concrete's been formed and poured back. And so they're doing the columns first. You can see similar, the columns done here and the columns done here. And if you look further in the background back here, you can see columns, and the pier caps are also finished all the way back there. So they're basically doing the columns first and then following along with a second crew doing pier caps. And obviously for these ones up here, they have not started the work on the pier caps. On the caps, they're doing basically the same thing as on the columns. They're removing the existing concrete cover, basically down to the reinforcing steel. They are putting some supplemental steel in where it's deemed required by the structural engineer. They're putting galvanized welded wire mesh for reinforcement in the overlay or in the encasement. The galvanic anodes in this case are the green kind of colored bars that are spaced out here in the horizontal orientation. And then they're forming and pouring using self-consolidating concrete, the section by section as they're doing the work. And there are certain staging requirements on the beams, but basically they're doing the full length of the beams using this method. And here's a picture of that first phase, the Jarvis to Cherry section near the end of the work. And here you can see the columns and the pier caps are all complete, and the substructure work is finished or near finished at the time when this photo was done. So that was an interesting project, and actually the second phase of this project has been bid and has been awarded, and the contractor is just getting set up to start the next phase, which is another section of this elevated section of highway. So that's, I think, the fourth case study. And I wanted to move from there and just close the seminar by talking a little bit about sustainability and how this work, doing the work this way, is a sustainable practice. And so obviously, you know, if we keep structures in service or keep them in service longer, you know, we have a lot of benefits. We talked about that at the beginning of the seminar, but we also reduce the demand for new concrete and other construction materials, and that is clearly a good thing. It's not necessarily easy, but it's certainly possible to do if we make it a priority. And we can quantify these benefits, and that's what I'd like to show you in the next few slides. So first, if we want to quantify things, we need to think about, you know, concrete as a whole. You know, so we make a huge amount of concrete in the world every year. It's the most widely used man-made building product in the world. We make about 6 billion tons of concrete every year. And to make that volume of concrete uses a lot of raw materials and energy, okay? And because we're making such a large quantity of concrete, there is a significant environmental impact that results from that. And that environmental impact can be quantified. Overall, to make 6 billion tons of concrete produces about 1.5 billion tons of CO2 every year and creates other emissions that can also be quantified. And in addition, making concrete, large volumes in particular, it also results in direct thermal pollution where we're dumping waste heat into the environment as well. So I am not in any way saying that concrete's a bad material. In fact, concrete is probably the most environmentally friendly material that we have available to us, but it needs to be used properly. Okay, concrete has the ability to last for many years. It has the ability to be very durable. And if we keep it for many years, its environmental footprint is much lower than that for steel or wood or these other building materials. But if we only use it and use it for a very short period of time and then demolish it and replace it, concrete is probably not a good choice for those applications. And so just taking this last project that I just talked about, the Gardiner Expressway project, we can quantify, what exactly is the benefit that can result from doing this. So first of all, you have an existing structure, at least for the substructure. They want a 40-year service life extension to the substructure. That's quantifiable. Okay. The substructure alone, just the substructure of that bridge, has over 70,000 cubic yards of concrete. And that, by them doing this repair and service life extension project, instead of demolition, that 70,000 cubic yards of concrete was maintained in service, and that 70,000 cubic yards of concrete was not demolished and not replaced by another quantity of concrete, possibly the same quantity if the bridge was rebuilt using the same design. And by not making another 70,000 cubic yards of concrete, the City of Toronto reduced their CO2 emissions by over 35,000 tons. And to put that into perspective, that's equivalent to the annual emissions of over 7,000 people. I heard at the beginning of the webinar, there's 600 and something people signed up for the webinar. The total annual emissions for more than 10 times the number of people that are on this webinar were eliminated by the City of Toronto making the decision to extend the service life of the substructure of this bridge. So these are quantifiable numbers and they do add up. I mean, this is a big job, yes, but it's only one project out of many, many projects that not only the City of Toronto is doing, but think of all the other owners and agencies. The possible benefit here is very large. If any of you are interested in quantifying these numbers for any of your own projects, you can go to wesafestructures.info. It's an informational website, and on that website there's a link to an online calculator. Screenshot is shown here on the right, and you can input the details for your structure in terms of the amount of concrete that you're saving, and just push enter, and it will calculate, the carbon dioxide footprint, the amount of concrete rubble that is produced by demolishing it, the amount of potable water that's used in the new concrete that would replace it, etc. And so all of this is quantifiable, and you can do it on your own projects and use that as you consider things. So with that, I'd just like to summarize, and first by saying thank you for the opportunity to be here. But Galvanic concrete encasements for accelerated repair and service life extension provide significant benefits. They're definitely beneficial for the owner. They're beneficial for the traveling public, and they're beneficial for the environment as well. The repaired structure must, and I'd say in most cases, continues to carry loads. That's one of the advantages of this technique. The repaired structure must last for the design service life. That's key. You need to define what service life you want, and then you need to do your design in order to achieve it. And you may need to do concrete repair, you may need to do strengthening, you may need to do corrosion protection. All of that is going to depend on your design, but you're going to have to do whatever is required to have a holistic design to meet your design service life so that you get the service life extension that you want. And finally, substructure reuse, but honestly, reuse or service life extension of any structure that's out there is a sustainable practice and provides environmental benefits. Thank you for your time today. It's a great honor to be able to present to this group, and if you have any questions, I'll be happy to answer them at this point. Thank you.
All right, Dave, thank you for a very interesting presentation. If you could turn your camera on. And so at this point, we are going to turn it to Paul Lyles and Rick Liptix to moderate the question and answer period. And based on the number of the questions that I saw that was coming on the dashboard, we are going to try to go up to 20 minutes after the hour. And if some of you have to leave a little bit early, the copy of the video basically is going to be posted on our website. Okay, so Paul, it's all yours.
Okay, thank you, Torrid. And David, can you hear me okay?
Yeah, for some reason, yes, I can hear you, but for some reason it's gone off of speaker onto the things. So I'm going to just hold my phone up to my head so I can actually hear you.
Okay, that'll be good. The first question we have, are there any non-destructive tests performed before executing the work?
Okay, yes, the answer is definitely yes. I shouldn't say definitely. I would say it would be highly recommended, yes. I would suggest, obviously, you should do condition survey of the existing structure, including the existing concrete damage, which can be done anything from chain drag through to GPR, hammer sounding, whatever. You should probably do chloride testing if you're in a chloride environment. And in many cases, I would recommend if corrosion is a problem, then corrosion potentials or corrosion rate measurements would also be good.
Okay. Is there any software involved in designing the system?
There are some programs available in terms of designing like for the service life of, so it's, I think, okay, maybe we should break that question into two parts. The first part is you need to look at the structural design and making sure that you're structurally in good condition through each of the stages of the repair. And you would use your normal structural software for that. And then I think if you do get involved in, say, a galvanic encasement and you want to design it for a certain life, then you need to also look at the performance and the service life of the anodes over time. So you're going to look at and do a design using like the NACE criteria to make sure that you have enough anode there to provide protection for the service life that you want in the environment that your structure is in.
Okay.
Yeah.
Is this repair system compatible with structures reinforced with pre-stressing steel?
Excellent question. Yes, if you stick with the galvanic encasements, they are compatible with pre-stressing steel. I showed at the very beginning of the presentation beam end repair, which was a pre-stressed concrete girder beam end, which was done very poorly and was failing. There's many situations like that where you can do a galvanic encasement and it's very effective. You would not want to go, I would not recommend that you go down the path of doing impressed current or an electrochemical treatment on pre-stressed or post-tensioned concrete structures because of the risk of hydrogen embrittlement, but galvanic is fine for that.
Okay. Question here, now these came in before the webinar, but here's one, and we had another person that asked it during the webinar. Please discuss unit cost or square foot cost of the material and installation of the anodes.
Oh, yeah. That's an interesting question. It's probably like asking how much does a bridge cost? Some are more, some are less. Trying to think how to answer that in simple terms. I mean, basically, I would say when you do your design, the design is going to be based on the amount of steel that you're trying to protect and how corrosive the environment is. So, for example, how high your chloride level is and how long you want it to last. Those are the three main factors that are going to influence either the number or the size of anodes that you're required to meet your design objectives. And if you want it to last longer, then obviously the cost is going to be more because you need either more or bigger anodes, as an example. If the steel, if it's a bigger structure or more heavily reinforced, you'll again need more anodes or bigger anodes to do that. I would say in most cases, this is far less expensive than removal and replacement. It's certainly more expensive than just doing concrete repairs by themselves. Depending on the situation, it's hard to say. I mean, it might add 30 or 50% maybe to the concrete repair cost, but you're going to have to look at that on a case-by-case basis, because there will be cases where it's only adding 10% and there's other cases where it'll be more than doubling the cost of the repairs. It depends a lot on the details of the job.
Okay.
Yeah.
Is chloride removal required prior to repair?
No. In fact, that's probably the main advantage of this.
Okay.
You are, in most cases, I'd say, leaving chloride contaminated concrete in place and saving the cost of removing and replacing it by putting in anodes, or you're leaving in place because structurally it's carrying load and makes things very difficult from a shoring point of view if you removed all the chloride contaminated concrete.
Okay. Is there a maximum amount of residual chloride allowed for the system to be effective? Could it be overwhelmed if there was too much?
Not really. I mean, you have to take that into account in the design. So if you have more chloride, you're going to end up with more anodes. But I mean, Florida DOT is using this technique on coastal bridges in Florida. We've done the same technique, not in bridges, but we've done the technique in salt mines and salt handling facilities. So they're very heavily chloride contaminated. You do end up using more anodes in those cases, but yeah, there's probably not really there's no theoretical limit on the amount of chlorides that could be there.
Okay.
Yeah.
What efforts are being made to realize design service life, say 120 years, used in the life cycle cost analysis to justify the project cost?
Sorry, can you clarify the question again? What efforts?
It says, what efforts? How can you, when you come out and say it now has 120 years life?
Oh.
How confident are you on that life cycle cost?
Okay. No, that's fine. That's
project cost.
Yeah. No, that's a good question. So we have probably over 25 years of field data for these systems installed and running in the field. So we have a good base of data for not 100 years, but certainly for 25 plus, and systems that are still running. And we can use that for design. I would say, we're not looking, generally speaking, you're probably looking at something that's, if you have an existing structure that's, say, 60 years old, like the Gardiner Expressway, or it's about almost 70 years old now, 65 or something, they're looking to get an additional 40 years out of that structure. And I think that's probably the way you look at it for existing structures. You know, it has a certain life right now. It's in a certain condition right now, and you want to buy a certain amount of additional time. I would say any numbers there between, or say 20 and 50 years is probably, you know, reasonable and designable. I would say anything beyond 50 years would be speculative at this point in terms of, you know, we have field history for 25 plus a little bit, but, you know, you could probably, with confidence, you know, you know how it's behaving. You can extend that by a certain factor, you know, 30, 40, 50 years probably is reasonable. But, you know, to say you're going to get a 100-year service life extension on something that's already there right now, we can do the design, but there might be enough uncertainty in it that you can't guarantee that life.
Okay.
Yeah.
Now, and yeah, this is common in some of the questions. One more that came in beforehand, then we're going to get to the ones that came in for this during the presentation. Can this system be applied to vertical planes? And I think you showed it.
Oh, yeah.
And
Yeah,
also
no.
you had overhead
And,
jobs too.
yeah,
Okay.
yeah. We actually started doing this on horizontal deck surfaces, like the top surface of decks, and then have moved from there to more vertical surfaces. And as you said, the underside of the deck as well. Underside's probably not so common, but vertical surfaces and top facing surfaces are definitely
Okay.
common. There's lots of them out there.
The other part of this question is, can it be applied underwater?
Yes. In fact, there's several jobs with Florida DOT that have this. Generally, in underwater applications, it's done in conjunction with a stay-in-place form. So it could be a fiberglass or a PVC stay-in-place form. And that's, yeah, Florida's got quite a number of those jobs, and Caltrans has a couple. Anyway, there's a number of them around that are underwater.
Okay.
Yeah.
You don't have to dewater it or anything. You can really do it
No.
underwater. Okay.
Yeah, I mean, generally what most of the agencies are concerned about is usually more like the tidal zone and the splash zone, so it's underwater periodically. But they can extend further down underwater as far as you want, but the area they tend to have the most problems with are kind of at the water line and just above the tidal zone.
Okay.
Yeah.
You had the pictures of the deck patch, and this question related to that. And it says, is the anode protection needed for all patch repairs, or is it just for specific cases? And what is the criteria to use or not use for the anode protection in the patch repair?
Okay, well, so if your patch repair is because of just concrete deterioration, like something like freeze-thaw deterioration or ASR, then there's no need at all for anodes for sure, because it's not corrosion related. If the corrosion is due to like carbonation, which tends to be a really slow kind of corrosion and very uniform, you can use anodes, but it might not be as high of a priority if the corrosion's because of chlorides, particularly if you have high chlorides. Then corrosion tends to be fast and very concentrated, and that's probably more where you'd want to focus on that. And in terms of design or spacing of the anodes, generally that's done based on the steel, like the amount of steel that's to be protected. So if you have more heavily reinforced structure, you calculate the steel surface area and you'll come up with a certain spacing. If you have a more lightly reinforced section, then you calculate the steel surface area in that section, and the spacing between the anodes will be wider.
Okay.
Yeah.
Here's an interesting question. Do the galvanic anodes form a layer of corrosion like the steel reinforcement does? And aside from not corroding the reinforcement, wouldn't the embedded anodes do the same as the steel in terms of expanding and eventually breaking the concrete?
Aha, this is a very good, interesting question. Okay, so the first part of it, the anode itself is corroding. It's passing current to the steel. Very often, you might, if you open it up, you might see that the form of the rust that is on the rebar might change from being kind of orange or reddy brown rust to being more black, like the mill scale. That's quite common. That happens over time. But the anode itself is corroding. And so to the second part of the question, that zinc that's inside the anode is corroding, and it's turning from being zinc into being zinc corrosion products over time. So the zinc is essentially rusting inside the anode instead of the steel rusting. And the anode, there is a slight expansion that happens. Fortunately, zinc doesn't expand as much as steel. It expands maybe 20 to 25% by volume compared to steel, which, depending on the chemistry and the environment, can expand 3 times, 4 times, 5 times in volume. So the expansion of the zinc isn't as much, so that's a beneficial thing. But even with that expansion is compensated, so there's porosity that's built into the anodes to accommodate the anode corrosion product. So the corrosion products have a place to go without creating an external expansion pressure on the concrete itself.
Okay.
Yep.
The question came in several times. What is the anode material on the bridge abutment? And you said zinc a minute ago.
Yeah.
So
So the anode material itself, the part that's corroding, is zinc, and generally, or most of these types of anodes, it's high purity zinc. But that's like half of the anode. That's the part that's corroding. The other part, which is really important for the functionality of the anode, is the material that is around the zinc. And for most of the anode examples I showed you, in fact, I think all of the anode examples I showed you, those are alkaline activated anodes. So there's a high pH mortar that is around the zinc, and it creates an environment where the zinc will continue to corrode over time and not passivate. So the purpose of putting the anode in is so that it corrodes and it continues to corrode over time. And we don't want the zinc passivating, which is just a fancy way of saying stop corroding. We don't want it to stop corroding, because then it's not working as an anode anymore. It's just an expensive piece of aggregate that's sitting inside your concrete.
Okay. By having anode protection, is it required to use epoxy-coated bars, or can black bars be used instead?
Yeah, most of the time black bars are used instead. Probably that question goes back to the photo near the beginning, where on the Ohio DOT example in 2005, they used epoxy-coated bars for the new steel in the abutment. The anodes are there to protect the black bar that's in the original abutment, and Ohio DOT, the research people that we were working with at the time, wanted just to use black bar for the encasement as well. But because Ohio DOT had their standards at the time, which was just epoxy-coated rebar, it was too much trouble to change it, so they just used epoxy-coated rebar in the new concrete section. But you can use it on either. There are some places where this work has been done on epoxy-coated rebar structures. You may have some additional work in order to make the individual bars electrically connected together, but it can definitely be done on black bars as well, for sure.
Okay, it's a quarter after. I'm going to go ahead and turn it over to Rick. We've got a bunch more questions here, and they're all good. Rick, you want to come in?
Thanks, Paul. Yeah, let's see, David. I got a couple of things here. What is the maximum life extension? What's the limits on the anode bars? Is there 40 years or what? I had a couple questions where wanting to know how long these sacrificial elements are good for.
Yeah, like I know for example, New York State DOT has used in a number of their specifications 50-year service life. That's probably at the upper end of, I mean, in theory, you could design for longer than that, but just in terms of how exactly it's, how you extrapolate the behavior over time, I think anything less than that is probably reasonable. A lot of DOTs are using 25 years as a standard. Like you saw in the last case study, Toronto, they were using 40 years on the Gardiner Expressway job. I would say anything in that 20 to 50 year time frame is probably reasonable.
Okay. Yep. Has there been any case studies or evidence where this technique didn't work?
Oh, that's a good question. Well, where it didn't work, I would say obviously probably if the anodes are not electrically connected to the steel, and there certainly have been some limited cases where maybe quality control wasn't done during construction, and and then investigation was done later and found out, yeah, the anodes were there, but they weren't actually connected to the steel. That certainly would be one case. If you took the anodes and cast them into like a very, very highly resistive material, like a epoxy mortar, for example, that would basically, you wouldn't be able to pass the current from the anode through the concrete. Those would be probably the two most common things that could lead to a failure.
Okay.
Yeah.
Okay. Let's see. Some instances there's a lot of development in the area of UHPC to seal up, like in shotcrete and different things. And I guess I'm wondering is if the question came up is that an alternative to some of this to the galvanic anodes?
Well, I think UHPC is a really good overlay material. Maybe in some cases even could be almost thought of as a coating. But if the concrete underneath the UHPC is already chloride, like salt contaminated, you might slow down the corrosion underneath the UHPC, to the extent that it helps, keep some of the moisture out, but you've got enough moisture and humidity around that corrosion is going to continue. And I would say it would probably behave similar to, there's been a number of research studies done, 20 years ago when FRP wraps were coming out and they were becoming popular, and some of the suppliers were going around at that time saying, well, if you wrap this thing with the FRP wrap, then corrosion is going to stop. And that wasn't what any of the studies actually showed. In some cases they slowed down the corrosion inside, but in no cases did it stop. And
continue.
And I would think if the problem's already inside behind whatever it is you put on as a material, you're going to still have it continue.
Quick last question. Is there any instances where you would apply this anodes to new construction, let's say?
Yeah, no, that's an excellent question to end on. I mean, the focus here obviously was on extending the life of existing structures. That's by far the most common thing over here. There have been a few small projects when I say over here, I mean North America, where it's been installed on new structures like seawall type structures, marine structures where they have corrosive conditions. There was a jetty down in Puerto Rico that they put anodes in from new because they had to replace the old one because of corrosion. In the Middle East, it's much more common actually to put anodes in on new construction because they have a really corrosive environment. But it's not the only option. There's lots of other options if you're building new construction, but it is certainly possible.
Okay.
Yeah.
Well, I think with that, we're gotten to the end. I don't know if Kathy or Adirad wanted to say anything.
I think I think that probably brings us to end of our webinar today. If there is no additional questions, and like it was mentioned, we didn't have a time to really provide the answer to all the questions, but we will be getting the answer to all the questions that were posted or sent on the dashboard and post them on our website. So on that note, we're going to conclude our webinar and hope to have you back with us next month. Thank you.
Thank you. Thanks, David.
Thank you very much for the opportunity, and have a great afternoon, everyone.